to another lecture. So today we will be continuing with torsion itself, but regarding how to solve torsion problems using strain energy approach. Before I proceed, I will clarify a doubt which was asked by a student based on previous lecture. So let's go to lecture number 9. So if you remember correctly, one of the things that we said was in the final derivation of MT, we had taken phi as 0 along boundary. Okay, so how is that possible? That was asked. See, first of all, what we have to understand is these are the two equations that we had arrived at in terms of stress function. So second equation states that the bound ds d phi by ds equal to 0, which means the derivative of phi with respect to s is the boundary, s denotes the boundary, is 0. So from calculus we know that if a derivative of something needs to be is 0, then the function itself should be a constant. Okay, now what is seen is that I think I have also missed to state that point. So one thing is sure, phi should be a constant along the boundary. Okay, that is what this equation says. And in the case of solid sections, okay, see, we know that there are different types of solid sections, right? There is annular section, solid section, channel section, many types of sections. So when you have a solid section, like what, let it be of whatever shape, parabolic, elliptical, square, rectangle, whatever, as long as it's solid, the phi can be chosen arbitrary. So in the case of solid sections, we take phi as directly 0 at the boundary. Okay, because this equation tells us that it should be constant along boundary. So if it is a solid section, we can directly take it in addition to being a constant, we can take it as 0 itself. So that is how I have used phi equal to 0 along the boundary, assuming that this derivation is for solid section. Okay, so just keep that in mind, just wanted to clarify that. So proceeding with today's lecture, so this is one more topic straight away mentioned in your syllabus. So basically till now in the last 3 lectures we were dealing with the solution of torsion problem in terms of stresses. So let us discuss, how does the solution change when you deal within strain energy. So you might also recall that even when you learned structural analysis, you might have learned many ways of analyzing indeterminate structures, right? So one of the methods of analyzing is by using energy approach. Okay, so whatever we are discussing, you can draw some parallel with it, and including some of the concepts like virtual work and things like that, which I learned it in the past in the structural analysis subject. Okay, so let us see how the solution is. So in the case of stresses, we had seen what it was. So basically our problem reduces to these two equations if it is stress function approach. So second is boundary condition, and then you have this equation. So you have to find out a stress function phi which satisfies boundary condition and this equation. That will be the solution for the particular problem. So this is the stress approach. So now we are trying to find out the solution using strain energy approach. So first of all, let's see what is strain energy. The equation of strain energy is half into stress into strain into volume. So you might have studied this particular expression. So where half is for the gradual loading effect and things like that, but anyway, it is half into stress into strain into volume. Now in the case of torsion problem, we had already seen, see, this is the problem that we are trying to solve, right? You have a twist at the end. So we had already seen that only non-zero stresses are tau yz and tau zx. So when you write the expression for strain energy, only those two stresses will be there. Okay, so these are the stresses, tau xz, tau yz. Strain if you know the stresses, so remember these are shear stresses. So the corresponding strain, you can write it if you know modulus of rigidity as tau xz by g, tau yz by g, right? So you know stress, you know strain. So let us write the expression for strain energy. So let us write the expression for strain energy in, per unit length. So instead of volume, we will be dealing with area, and z component or the length component we will ignore because we are writing in terms of strain energy per unit length. So as I said, only two stress components will be there. So you will have two terms. So stress into strain, this is stress, this is strain. So square will come because you have two terms which are similar. So this is square, half is outside, g is modulus of rigidity which is common for both, and dx dy. So basically this is strain energy per unit length, which is an integration throughout the cross sectional area of this particular expression. Okay, so now tau xz and tau yz, we know their formulas in terms of stress function. So I'll go back to that. So remember in our derivation, these were the expression for tau xz and tau yz. So you can substitute that into this particular equation. So the equation simplifies to this form. Okay, so remember this is the strain energy per unit length of the shaft or the bar or the cross section which you are trying to analyze. Now, similar to the principle of virtual work, let us give a small variation in stress function, okay, which is compatible with the boundary conditions. So you phi is the original stress function, so you give a small variation, okay, virtual variation. So the change in strain energy or the variation in strain energy will be this, where see 1 by 2g is a constant, right? So the only change delta will correspond to this expression which is inside the integral. So this is the variation in strain energy due to the small variation in phi. Now you might have again studied the concept of external strain in change in strain energy is external work done and things like that, right? So we'll use the same principle. So this is the variation in strain energy. So this should be equal to change in external work done. Now remember the cross section is subjected to the external moment mt, right? So this is the cross section, so it is subjected to external moment mt. So the external work done is nothing but mt into theta, right? So first of all, let us write the expression for mt. Expression for mt is 2 double integral phi dx dy, which we had arrived at in earlier lecture. Now just like here we are giving a small variation of phi, right? And this is the change in or the variation in strain energy. Similarly, this expression for this original expression for mt. Now if you give a small variation of phi given by del phi, same magnitude, the variation mt or the change in mt will be 2 double integral del phi dx dy. Okay, so now the work done due to this variation mt is, remember, moment will cause rotation. So if mt is the external moment, it will result in a work of moment into angle of twist. Okay, so here theta is angle of twist per unit length. Remember our earlier definition of theta. Here we are defined as the twist per unit length. So the work done per unit length is nothing but mt, variation mt into theta. So variation mt is this, so to that you multiply theta. So this is the work done during the variation phi. Now just like you might have done, many times in the virtual work principle and things like that, you equate the change in strain energy to work done. So this is the expression. Okay, so you can take things to other side. So this delta or the change in this function and this function, you can write it common. So the variation in this total expression should be equal to 0. Okay, so which means our solution corresponds to, now this is the equation that we are trying to solve. So remember this, so in this expression, the only thing variable which is again phi, right? So phi or stress function is our pivotal point, even if whether it is stress approach or strain energy approach. So other things are known. So the phi or the stress function, again, if you recall, whatever we done so far with stress function is, initially it is a guesswork, right? You have to start with a starting approximation of stress function which will satisfy the equation and boundary conditions. So the phi or the correct phi which corresponds to solution of the problem is the one that satisfies this equation. Okay, or you can say it is the stress function which makes the variation of this particular integral. So see, delta, this integration means variation in this particular integral. So that phi is, this correct solution is the phi is the one that makes this variation 0. Okay, now let us now the question is how to start with phi. Now earlier approaches and all, we have started with a phi that is using, which satisfies the boundary condition and things like that. Now one of the more robust ways of solving this problem is by assuming a phi in the form of an infinite series. Okay, so phi is already an unknown. Now we are writing in terms of an infinite series, a constant a0 into phi 0 plus a1 into phi 1 plus a2 into phi 2 plus etc. So phi 0, phi 1, phi 2 are stress functions which should satisfy the boundary condition. Obviously phi should satisfy the boundary condition. So phi 0, phi 1, phi 2 etc. should also satisfy the boundary condition. And if it is a solid bar, as we had already mentioned, it should be 0 along the boundary condition. So that is the boundary condition that it has to satisfy. So all these individual stress functions or individual terms in this should satisfy the boundary condition. Now a0, a1, a2 are constants which should be evaluated. Now how you can evaluate it? For that we will use this condition. So remember, the correct phi is the one that ensures that the variation of this integral is 0. So mathematically speaking, it reduces to this form. So each of the coefficients. So now what happens is, see, you can write it in terms of phi. Phi is this. So this expression for phi, you will substitute in this expression for u. Now to make this a minimum or to make the variation 0, individually with respect to each coefficient, the strain energy should satisfy the following expression: del u or partial derivative of u with respect to, sorry, it's not strain energy, it is the resulting expression. Strain energy is actually the original expression, but anyway, so this expression for u, the partial derivative of u with respect to a0, a1, a2, individually they should be 0. Okay, so if you try to apply this condition, so remember in the expression for phi itself you have a0, a1, a2. So if you try to individually write these conditions, you will get n number of linear equations using which you can solve for all these individual constants. So how many, depending upon how many terms you are taking, that many equations you will get. So you will have as many equations as the unknowns to be solved, using which you can solve for a0, a1, a2 etc. So once you solve for a0, a1, a2, etc., you can plug it in this particular expression and you will get the final expression for phi. Now when you get the expression for phi, remaining all the things you can solve that we have seen. So obviously as you increase the number of terms, the accuracy of this will increase. So when you consider infinite number of terms, it will be the actual solution. And we have seen that even trigonometric functions like sine and cosine, they can be written in terms of infinite series. So if you are writing those infinite series as a specific, means if you are as the number of terms increases, it means it is converging to a specific function, right? So as you increase the number of terms, it will increase the accuracy. Okay, so this is in nutshell the strain energy approach. So what you do is we have to ensure that the variation of this integral is 0. So we assume stress function of the following form where phi 0, phi 1, phi 2 satisfy the boundary condition. So a1, a2, a3, etc. we will evaluate it by solving the set of linear equations. Plug it in this equation, we will get the expression for phi, using which we can determine everything else. Okay. So easier said than done. All these things might look a little hazy to you. So let us try to solve a particular problem. Okay. So let us try to solve the problem of rectangular cross section in terms of the strain energy approach that we already discussed right now. Now in textbook Timotion Go, it is section number 97 on page 280. Okay, so you can go through that. Whatever I discussed right now, a summary of that is already there. Okay, coming back to the lecture, let us try to apply this approach to a rectangular cross section. So you imagine a rectangular cross section of the following form: AA, BB, subjected to torsion. So remember, the fundamental problem that we are solving is same. Okay. So here, instead of an arbitrary cross section, we are taking a rectangular cross section of the following form. Now, so first step is in solving this approach is you have to arrive at a suitable expression for phi, where a0, a1, a2, etc. are constants. And one of the things that we said is this phi should satisfy the boundary condition initially, because ultimately this phi also should satisfy the boundary condition. So in the case of solid bars, we had already said in the start of this lecture as well that first of all, in the case of any bars, phi is a constant along boundary. If it is a solid bar, you can take it as 0 along the boundary. So our expression for phi, stress function chosen for a rectangular cross section like this, should be such that the phi is 0 along boundary. Now we know that if you take any function of the following form, x square minus a square into y square minus b square, automatically when you substitute x equal to plus a minus a, y equal to minus b plus b, this is always 0 along the boundary. Okay. So let us take the stress function in the following form. This particular expression, which is always 0 in boundary, into double summation a constant amn x raised to m y raised to n. Okay, where m and n are individual summations, it can go up to large number of terms. So first condition is satisfied. This phi chosen is satisfying the boundary condition irrespective of how many terms you take. Okay, so that is fine. So let us try to solve this. Now as a starting point, let us take just one term. Okay, so if you are taking just one term, remember first term we are noted as 0th term. So you substitute m equal to n, m equal to 0, n equal to 0. So this will be 1, amn or a00, 0, you can write it as a0. So this is our stress function. Okay, so using this stress function, uh, let us try to work on the problem. Now, in this stress function, this part is known, right? This part there is no confusion about. Now, the only unknown is A0. So, what is A0? For determining A0, we will follow the following procedure. Okay, so first we will write U in terms of stress function and take the derivative of U with respect to the constant and equate to 0. So in the general case you will have n number of equations. So here there is only one term and one unknown. So you only have only one equation to be solved. Okay, so this is the expression for U. So let us write it in terms of, there are two parts, right? There are two parts for the expression. So let us separately denote it as I1 and I2 so that we can calculate it separately because it works out to be a large expression. So first let us evaluate I1. So for I1 you declare del phi by del x, del phi by del y. So this is your phi. You take its derivative with respect to x, y, separate it, substitute it separately, and you integrate it one after the other, first with respect to x, then with respect to y. Of course, it is integration with respect to polynomials. You might have seen this many times starting from year +2, so I won't be going into details of this. So finally, when you simplify I1, the term for I1, you will get it in the following form. So this is your I1. So there will be A0 square. So where A0 is the unknown which we are trying to determine. So similarly you try to determine I2. Okay, this is I2. So it will simplify to following expression. So now you can use the condition del U by del A0 equal to 0. One equation, one unknown, using which A0 simplifies to the following form. Okay. So this is the constant A0 for the rectangular cross section that we are trying to solve. Okay, so we have A0, so you substitute that A0. This is the expression for phi. Now we can find out every term, right? So the problem is solved now. Now let us look at what will happen if it is a square section. So for the general case I have taken a rectangular cross section, that's why you have A and B separately. If it is a square cross section, A equal to B, right? So if that is the case, what happens is, if you substitute A equal to B in this particular expression, you will be A square, this will be A square plus A square. So this will be the expression for A0. You substitute that in phi, this will be the expression for phi. Now once you know phi, we will determine MT using this expression. So this is the final expression for MT. So remember, this problem is solved by taking only one term. Okay, and as we said, through its formulation itself, it is clear that the solution of phi is only approximate as long as you are taking finite number of terms. So how much is the error if you take only one term? So this is the expression for MT if you take only one term. So MT in terms of G and theta and half the length of side. So it is seen that this approximate solution has an error of 1/3% when compared to actual solution. So what is actual solution, that we won't discuss here, but this is just a rough number which I am giving you just to have a physical feel. So obviously this error will come down if you take more number of terms. So in this particular expression, if you, instead of one term, if you take 3 terms or 5 terms or 7 terms, as you increase the number of terms and do the same calculation, obviously it will be a very lengthy calculation, this error percentage will come down. Okay, so this is the lecture used this is the lecture in which we have discussed the solution of torsion problems using strain energy approach. Okay, so with this particular lecture we will conclude the topic of torsion in your syllabus, and from next lecture we will move on to the next topic. So the next topic is elastic plastic behavior. Okay, so if you have any doubts, please let me know. So although I have taken much of a time in today's video lecture, in concept what we have discussed is nothing much. Okay, so please go through the notes. You can also go through the textbook. If you have any doubts, please let me know. Thank you.